Today we're going to be talking about how to assign oxidation numbers. Now there's a couple rules you're going to have to follow. The first rule, the rules right here, unfortunately you are going to have to commit them to memory. They are that free elements, or things that are just in the element form, that's what free elements means, are going to be zero. So sodium when it's alone, in its elemental form, it's zero. When it's part of a compound, different rule. F, when it's F2, that's still not, there's no second or different element present, and so that's also zero. And even an extreme example like S8 would be zero, because even though there's 8 S's, there's no different element present to make it a compound, so therefore it still counts as an element, it's still zero. Now for the elements, we've got group 1 plus 1, group 2 plus 2, F minus 1, H plus 1, O minus 2. And the easiest way to remember it is you can see it right here. Group 1 is really from lithium straight down. They're all going to be plus 1. Group 2 is from Be straight down. They're plus 2. And then we have rules for F, H, and O, and that is it. Those are the only ones that have rules. Now, what are we trying to do with these rules? Well, we are trying to make the sum of the individual charges of the elements add up to the total charge on the compound, which that should make sense, right? If you have a bunch of elements and they have charges, if you add up all their charges together, then that should equal the charge of the entire molecule. And that is what we would call conservation of charge. The charge can never be created or destroyed. So in other words, your total has to, when your individual parts have to add up to equal your total. That's just, that's pretty much how most things work in life, although not always. Now, the way you do this is simple. So here's a couple examples of compounds that we're going to do. Now, none of them have a charge written in the top right-hand corner. So we're going to assume that their total charge, just like an atom, if there's nothing written in, we assume it's zero. So since compounds, they're the same way. If there's no charge written in, we assume zero. Now, the next part, you're going to have a rule for one of these elements, sometimes more than one. You're going to write down the ones you have a rule for, and this is why the periodic table, having it out, is important, especially in the beginning. And then you're going to skip the ones that don't have a rule. We'll come back to them and do them later. So in this problem, sodium is in group 1, so it's plus 1. Nitrogen doesn't have a rule. F is minus 1. Fe doesn't have a rule. O is minus 2 when it's in a compound. Al doesn't have a rule. And for this one, O is minus 2 because it's in a compound, and Ca is in group 2 and in a compound, and therefore it has a rule as well. So now, we're going to look at the total charges. So the way that works is, I like to say it like this: multiply down, add across. That's like the real simple way of explaining it. So in other words, multiply down means that I have 3 sodiums, they're plus 1 each. So if I multiply those together, I'll get the total from sodium. Now mathematically, nitrogen's going to have to be minus 3, because this whole thing has to equal 0, right? So since there's only one nitrogen, I'll write it in now, but we would never write the ones. Since there's one nitrogen, it is going to get the entire minus 3, because that's the only way nitrogen will total minus 3 to make this whole thing 0. And again, that'll never be written. It'll look like that. You'll never have the 1 written in. For this one, there's 2 F's, they're minus 1 each. So if I multiply down, they give me minus 2. Mathematically, Fe has to give me plus 2. Since there's only one Fe, it gives me the whole plus 2. If that didn't make sense, it should make a little bit more sense when you see one where they're like this next one where there's more than one aluminum. So oxygen gives me plus negative 6 because there's 3 negative 2's. So if I multiply them together, I get negative 6 total from oxygen. So Al is going to give me plus 6 to make it equal 0. Well, since there's 2 aluminum, they are going to give me plus 3 each, because 2 plus 3's give me my plus 6. That's multiply down. 3 times 2 is 6. So for this one, oxygen is negative 2. There's 4 of them, so I get negative 8. There's 1 calcium, it's plus 2, so I get plus 2. So mathematically, I'm going to need this to be plus 8, so I can have minus 8 equals 0. 2 comes from calcium. The remaining 6 is going to come from chromium, which is Cr. There's only 1 of them, so it gets the whole plus 6. If there were 2 chromium in the equation, they'd be plus 3 each. If there were 3 chromium in the equation, they'd be plus 2 each. So you should hopefully get the idea. So that's how you do basic compounds. Next one, we're going to do ions. So the way ions work is they are pretty simple. They're going to, there we go, they have charge written in. So if you see this minus 1 or this minus, plus, and 2 minus, what it means is minus 1, plus 1, and minus 2. But now this isn't for the oxygen. They never actually write oxidation states for the individual elements because it would be too confusing with the total charge. They just write the total charge and assume that you then know or can figure out the oxidation states of the individual elements because you know the rules, because chemistry. So the way we do it, what it actually means is this. That's what that means. And that's what that means. So the way this works, it's pretty simple. It's the same thing, except instead of setting these equal to 0, because their total was 0 like I did in the first set, I'm going to set these equal to their charge, because that is their total now, because they have their ions. So I'm just using their total charge, and I'm setting them equal to that number. And then I do the problem the exact same way, except I'm just not going for 0 as my end result. So oxygen is -2. There's 6 of them. I get -6. So mathematically, this has to be 5 minus 6 equals -1. So I always like to put the pluses in. So +5. There's only one chlorine. It gives me the whole +5. For this one, there's a rule for H. It's +1. There's 4 of them. They give me +4. Mathematically, nitrogen has to be -3, so that I have -3 plus 4 equals +1, so I can make the math work. There's one nitrogen, it gives me the whole -3. Next one, -2 is my result. Oxygen is -2 on its own. This is a common mistake. Do not confuse the -2 in the top right-hand corner for the -2 for oxygen. That's kind of the reason why they write it 2 negative instead of -2 to make it less confusing. You can tell it's a little different. You know, that does work. Hopefully it helps, but if not, you just have to memorize it. So there are 2 negatives, or there's oxygen is -2. There are 7 of them. So that gives me -14. So mathematically, chromium has to give me +12 to make the math work. There's 2 of them, +6 each. So again, nothing different. It's just the end result is not going for 0. We're going for whatever the charge happens to be on the molecule. It can vary. Now, there are exceptions to these rules. So it turns out the rules for compounds, so rules 2 through 6 are, well, all of them actually, are in order of importance, meaning rule 1 is the most important, rule 6 is the least important. The reason we rank them in order of importance is because sometimes the rules break. So the way you're dealing with an exception, the way you know you're dealing with an exception is very simple. The math does not work. Watch how this plays out. So all these are 0 because they have no charge. So I'm going to set them equal to 0. That's true. But what I mean when I say the math doesn't work is this. When sodium's in a compound, it's +1. When hydrogen is in a compound, it's also +1. So I didn't like the fact that the plus was touching the 1. All right, made it look too much like a 4. So with these guys now, let's take a look. If I do this, I get 1 and 1 equals 2, not 0. So that's how I know I'm dealing with an exception. All of these will do it. If you look at it, you're going to get +2, +1, that won't equal 0. +1 minus 2, that won't equal 0. -2 minus 1, that won't equal 0 because you'll get -2 and -2, which would be -4. Here you'd get +2 minus 4, and here you'd get +2 plus 1. So you look at these and you say the math doesn't work. There's no way. So here's what we're going to do. We're going to take the least important rule on the grouping, right in this order, and we're just going to ignore it. That's literally what you do. You take the least important rule and you say, that's the rule I'm breaking because I need to make the math work because the law of conservation of charge is a law and I can't violate it. I can't just, make more electrons or protons than I have. So it's simple. Sodium is the higher rule. So hydrogen's rule goes out the window. Hydrogen again, calcium's rule is more important, so hydrogen's rule goes out the window. Here, oxygen's rule is less important, so oxygen's rule goes out the window. And here, oxygen rule is also the least important, so now it changes. So now it's going to change dramatically for some of them. All right, so let's take a look. And again, once the rule's out the window, it could be whatever it needs to be to make the math work. So here it's easy. It needs to be -1 to make the math work, so hydrogen goes -1. Here, it also needs to go -1 to make the math work, so I get -2 on bottom. Here, oxygen has to be -2 to make the math work, and then -1 each to make that happen, so it became -1. And this is the biggest change. Oxygen needs to be +2 to make this math work, so it goes +2. And if some of you have already caught on, these are violating the octet rule. If you remember the octet rule, right? This is like oxygen +2, not a happy oxygen. Oxygen normally wants to gain 2 electrons, and in this case, it lost 2 electrons to fluorine. The further you get away from the octet rule, the more unstable the compounds become, and the more dangerous they tend to be around. So, like, for example, this is hydrogen peroxide. It's the stuff in the brown bottle you get from the like a pharmacy. You put it on cuts and things like that. When you get it from a pharmacy, I think it's 5% or 3% hydrogen peroxide. The other 95% or 97, I forget what it is water. So and that still foams up and burns when you put it on a cut. When you can buy it, when it gets till over 30%, it can become explosive. Same thing with these guys. They're not exactly safe chemicals to be around, and I don't even know what this does, but I guarantee you it's not good. Or it's not a safe chemical to deal with. And so just because the oxygen is so far away from what it normally wants to do, I can almost guarantee you it's not going to be a safe or a stable chemical. Let's go to the back. So here's what's going to happen. The next part is these are dealing with polyatomic ions. So normally when you're doing these, you would run into a giant problem. When we do math at this level, we like to have one variable. Now, if you're really good at math, maybe you can deal with math problems that have two variables, but you usually need 2 equations to deal with 2 different variables and do what's called you get the idea. So it can be done. In chemistry, not really. And so for us, if we have 2 variables, then we are going to need to get rid of one of them, okay? And there are some sneaky ways we can get rid of one of them. Let me explain what I mean. So for these original problems, we would set them equal to 0, just like normal, because they don't have charge. That never changes unless they have a charge. Then we would apply our rules. The rule for oxygen when it's in a compound is -2. But that's all we have a rule for. In other words, we have 2 elements that have no rule. Now, if they were the same element, I could say, well, they're going to be equal because they're the same element, maybe, hopefully, right? There are some exceptions. But they're not even the same element. So now I've got 2 unknown variables. It's like basically, this is like me saying x plus y minus 8 equals 0. Well, I can't solve that unless I have a second equation, and I don't. So here's the trick. You go to your reference table and you go to the polyatomic ion chart, and we're going to use it to get rid of one of the variables. And here's how. SO4 is on the polyatomic ion chart. It's called sulfate. When it's alone, it's got a charge of -2. So what I can do is I can do this. I can say, well, that, when it's alone, is -2. So if I set this equal to -2, I use the rule for O, -2 for O, multiply down, I get -8. Mathematically, this sulfur in this equation is going to be +6, right? Here's the good part. Once you know that the S in sulfate is +6, then you know that the S in every sulfate in the entire universe is also +6. They're all the same. That's the deal about being a polyatomic ion. They don't change. They're too stable, basically, for the most part. And so, since I know it's +6, guess what I can do? Plug in that +6 that I just figured out, because there's only one sulfur, so it gets the whole +6. And now, reset this whole thing to 0, and I can solve for copper. So the way I would do that, multiply down, I get -8 from oxygen, I get +6 from sulfur, so I'm going to need +2 from copper. There's only one copper. It gives me the whole +2. So by using table E, I get rid of one of the 2 unknowns. That's the best way to do it. There is another way of doing it that I will show you when we get into naming chemical compounds that can be a little bit faster if you don't need to know. Like if I didn't need to know S and I just wanted to know copper, there's a faster way that I will show you a little bit later on. But sometimes you need to know them all. And when I say sometimes, I mean fairly often. And so you do need to know how to do it this way as well. So let's do this one. So nitrate, NO3, when it's alone is -1. I got that off table E. Set it equal to -1. Oxygen, when it's in a compound, which it still is -2. I get -6 from oxygen. So now I'm going to need +5 from nitrogen. There's only one nitrogen. It gets the whole plus 5. I can now plug it in up here. And now I set this whole problem equal to 0. And watch how this works. The 2 outside the parentheses doubles everything inside the parentheses, just like math. So there's not 3 oxygen, there's 6 oxygen. So negative 2 times 6. Let me just do this, different color. So negative 2 times 6 gives me minus 12. There is 2 nitrogen here from this 2. They're plus 5 each, so I get plus 10. Notice I'm only doubling the bottom numbers. I'm not doubling the top and the bottom. That's not how this works. This is only for the number of atoms that it's affecting. All right. And then the last part, since Fe is outside of the parentheses, the 2 has no effect. The parentheses, this 2 over here has no effect on it. So now I just mathematically, Fe, I need it to be 12 minus 12 equals 0. So Fe is going to be plus 2. There's only one Fe in this whole equation, so it gets the whole plus 2. Last one. PO4, when it's alone, it's called phosphate, is minus 3. I look it up wherever it is here. Right there. There it is. So now set the whole thing equal to minus 3. There's only one PO4 in this equation. So notice also I didn't do it here. The 2 outside of the nitrate, I didn't include it when I'm just trying to figure out the charge at the end. And same thing here. I'm not including the 2 outside. I'm just saying a phosphate, a singular phosphate on its own, is negative 3. That's what table E is telling me. Oxygen, when it's in a compound, is negative 2. That gives me minus 8. So mathematically, P has to be plus 5, or at least total plus 5. There's one P, so it gets the whole plus 5. So now I go in and plug in that plus 5 for that P, and I can figure out the rest. So now this equation has 2 phosphates. That's fine. What that means is I have 8 oxygen and 2 phosphoruses, right? And so when I multiply down, it's not 2 times 4. It's technically 2 times 4 times 2, or you could just say 2 times 8. Same math, I don't care. So minus 16 from oxygen, plus 10 from P, because 5 times 1 times 2, right? And then last one, the V does not, there are 3 V's, but there's not 6 of them. This 2 doesn't affect it. So the V mathematically is going to give me plus 6, because I need it to be 16 minus 16. There's 3 of them, so they are plus 2 each. So just keep in mind, this topic we're introducing this topic. We are going to use it for figuring out the names of chemical compounds, because turns out with these type of compounds, the name will change based on the oxidation state of the metals. And so that's a big deal. And then we will bring it back again when we get later on in the year, when we get into our redox unit, reduction and oxidation. So these numbers are, if you have to learn them now because you need them for naming, but you're also going to need them because we're going to do an entire unit basically on these numbers exclusively at the very end of the year. And so if you don't learn them now, you're going to end up learning them eventually. Now, these are going to be practice problems. I am going to include an answer key. So what I want you to do is I want you to do these guys. Remember, the ones, this first column, they all have no charge. You're going to set this whole column equal to 0. This second column, they all have charges. So you're going to set them equal to their charge. So in this case, it's minus 2. This one would be minus 2. This would be minus 1, minus 2, minus 1. You get the idea. And then these guys they don't have charge at all, so they're all going to equal 0, but these are a combination of exceptions and polyatomic ion practice problems for you to do. So these 2 down here are polyatomic. The reason I know is because there's 3 atoms, there's 3 different elements in them, and they're the only ones that will ever have more than 2 elements. And then these guys are exceptions because I happen to know that they're exceptions. So do the work, check them against the answer key, so that way you know you're making sure that you're doing them right, and then move on from there.